Here you 8-5 multiple choice practice problems. This looks like it's got chances to match up to a couple things, but the degree here is suggesting that maybe we should simplify by doing long division. X squared goes into x squared one time. X squared plus 1. We subtract that. That gives me a remainder of -1. So this is equal to antiderivative from 0 to 1 of 1 minus 1 over x squared plus 1 dx. And that's a pretty easy antiderivative to do. The antiderivative of 1 is x, and the antiderivative of 1 over x squared plus 1 is tangent inverse of x from 0 to 1. Plugging 1 in here, that gives me 1 minus the tangent inverse of 1 is pi over 4. Plugging 0 into those gives me 0 for both, and that's the same as answer choice A. It's equivalent to that. So notice you didn't have to play the A-B game. This is an interesting problem. You can do it using the A-B thing with the two factors here. This factors into x times x plus 2. But you can also do it using a U-substitution. The reason the U-substitution works is the derivative of this is 2x plus 2, which is 2 times the top. So a U-substitution would work in this one. But since we're doing partial fractions, I'll do it that way. So let's see. Myself a little more room here. We got a over x plus b over x plus 2. We need to get that top to match up to x plus 1. So it's me ax plus 2a plus bx plus 2, sorry, that's supposed to be an a there. And that's supposed to match up to x plus 1. So a plus b must be 1. Those are the x terms. And 2a must be equal to 1. So a is 1/2, and since they add up to 1, that means b must also be 1/2. So that means this turns into, since they're both 1/2, I'm going to factor the 1/2 all the way to the outside. So I get 1 over x plus 1 over x plus 2. Again, since they both had the same 1/2, I just brought that all the way to the outside. You can do that if it's the same factor. And that gives me, I'll just jump over to here. The antiderivative of that is natural log x plus natural log of x plus 2. I didn't bother with the absolute value signs because I'm going from 1 to 2. And if you plug those in, let's see what we get. We get 1/2. I'm just plugging 2 in. That's natural log 2 plus natural log 4. Since I'm adding logarithms, natural log 2 plus natural log 4 is natural log 8. All right, I can multiply them. Minus, plugging 1 in, natural log 1 plus natural log 3, that's natural log 3. You can either multiply them or realize that natural log 1 is 0, either way. And that matches up to b. If you do it by U-substitution, you'll get the same answer. All right. This is definitely partial fractions, this one. So let's see, a over x minus 1 plus b over x plus 2. So I've got ax plus 2a plus bx minus b has got to match up to, there's just a dx on the top, so that's like matching up to 1, which means the a plus the b, since there's no x term, a plus b must be 0, and 2a minus b must be 1. adding those together gives me 3a is equal to 1, or a is equal to 1/3. And since a plus b is 0, b must be negative 1/3. Right? So that means my original integral now turns into, again, since they're both 1/3, I'm going to move the 1/3 to the front. So I have the same factor. I get 1 over x minus 1 minus 1 over x plus 2. I just brought the 1/3 out to the front. And that is going to give me 1/3 times natural log of x minus 1 minus the natural log of x minus, or x plus 2 plus c. And using the logarithm simplification that says I can turn that into division, that matches up to answer choice A. Now, I'm going to save myself a little time here, since we actually just did you notice this is the same thing, just times 3? So multiplying that by 3, that means we're doing this from 2 to 3, right? And that's equal to, plugging the 3 in here, we get 3 minus 2 is 2 over 3 plus 2 is 5. That's the natural log of 2/5 minus the natural log of 2 minus 1 is 1 over 4. And using logarithm rules, I can combine those by division. That's natural log of 2/5 over 1/4. And dividing by a fraction, same as multiplying by the reciprocal. That matches up to answer choice D. Again, we cut a corner there because we had just done that antiderivative in this part. Let's see what we have here. This is similar to which one on the last page? The one where you can actually do a U-substitution here, or you can do the AB game to find the antiderivative of this. Why does a U-substitution? Maybe I'll do a U-substitution for this one and show you how it works. But you can factor this and do the AB thing. Oops, sorry. Got a step ahead of myself there. You make u equal to x squared plus 2x minus 3. And du would be 2x plus 2. Now, the reason that this is going to work is because 2x plus 2 is what you get if you multiply that by 2. That means I need a 1/2 on the outside. So, rewriting that integral, I get 1/2. Now 0 to 1 turns into -3 to 0, changing my numbers over to u numbers. And this all turns into 1 over u du. So that's 1/2 times natural log absolute value of u from -3 to 0. And that's natural log of, sorry, I forgot the 1/2. 0 minus natural log of 3. Notice the 3 gets made positive, but this is negative infinity, so it's divergent. You will get the same thing if you do the AB game. Alrighty. This one, you can go ahead and do the antiderivative here, and you have to realize that why is this improper? It's because it's going over 0 here, right? And 0 is a vertical asymptote of this. I really like to, whenever possible, think about things visually. And I know that the 1 over x cubed function looks like this. So 3 over x cubed really looks very similar. It's just got a vertical stretch like that. So they're asking for area from here to here. And well, I suppose that could exist, right? Because that could be an area that exists. But if you try the work, it would be, if it does exist, it's 2 times, since this graph is symmetric with respect to the y-axis, it's an even function. We could just test from 0 to 1, but what you're going to find is that it is in fact divergent. I'll let you do the work for that. And the last one, we've got the same function here. So let's see, the antiderivative of x to the negative 2 is negative x to the negative 1 from 2 to infinity. And I'm going to take the negative to the outside. That gives me 1 over infinity, that's infinity to the negative 1, minus 2 to the negative 1, which is 1/2. And 1 over infinity, that actually goes to 0, so this is not a problem. Negative, negative 1/2. That's A. So that does exist. Let's try to get the step-by-step in here too. All right, so this is step-by-step problem number 9. Average anything means we're actually finding a slope. So acceleration is change in velocity. Average acceleration from 0 to 4, by definition, and this is the definition we need to know, is this. V of 4 minus V of 0 over 4 minus 0. Now, it's a little messy, and I'm going to let you do the work, because I've already done the answer. I've already worked it out before. I'm plugging 4 into this, and 0 into this, and 4 minus 0. You get something like, let me see if I can find it. 7 over 30 minus 3/2 all over 4. Anyway, it all simplifies to minus 19 over 60, which is my lucky number, just coincidentally. Part B, find the intervals where the particle is speeding up and slowing down. Okay, well, we're only talking about times greater than 0, and so looking at the velocity function and this, the velocity function has 3 factors in it that have the possibility of changing the sign, right? Because any combination of signs here. But notice if you plug in positive t values, all 3 of these factors are always positive. So although this does change signs at -1, -2, and -3, it doesn't change signs anywhere for positive t values. So the velocity is always positive for all values of t. The acceleration, doing the quotient rule, let me see what we have there. You end up with this, negative t squared plus 6t plus 7 all over t squared plus 3t plus 2 squared. You can go ahead and do the quotient rule on that and see if you can get it to match up to this. Now, let's take a look at this and see if we can figure out where this would be 0. Well, this is always positive because it's getting squared, right? Now, this is going to determine whether it's positive or negative, right? So let's go ahead and, this doesn't factor. So using the quadratic formula, we get minus b plus or minus the square root of b squared minus 4ac all over 2a. A is 1. So that gives me minus 6 plus or minus, let's see, 36 minus 28 is 8 over 2. which is negative 3 plus or minus the square root of 2. Now, we're only looking for places where it crosses, where we have positive values. Now, negative 3 minus the square root of 2 is certainly negative. And negative 3 plus the square root of 2 is also negative. So this thing only changes sign also when it's negative. That means it's always going to have the same acceleration. And taking a look at this, we plug in positive t values here. And this is positive, this is positive, this is going to make it negative. So velocity is always positive, acceleration is always negative. So that means the particle is slowing down forever. From time 0 to time infinity. It's forever slowing down. It's kind of sad, I guess. Now, find the position of the particle. If we want to find position from velocity, we have to do the antiderivative. So now we're going to have to play our AB game. This is t plus 1 over t plus 2. So a over t plus 1 plus b over t plus 2, and it's a t plus a plus b t, oops, that's 2a there, plus b, that's got to match up to t plus 3, so a plus b has got to be 1, and 2a plus b is 3. And subtracting this equation from this one, doing a little Gaussian elimination, and a is equal to 2, so b must be negative 1. Alright, so that means our original integral turns into 2 over t plus 1 minus 1 over t plus 2 dt, which is equal to 2 times the natural log of t plus 1 minus the natural log of t plus 2. Since I'm only dealing with positive t values, I didn't need absolute value signs. You can put them there though, that's fine. That's my position function. That's my x of t function, my position. Now they gave us a point, 0.01, so I'm supposed to solve for c here. So plugging 0 in here and solving for c, I'll let you do that. You should get a c of 1 plus the natural log of 2. So that means my position function finally is 2 times the natural log of t plus 1 minus the natural log of t plus 2. You could consolidate those by division if you wanted to, plus 1 plus the natural log 2. That's our position function. That's the c when you plug in the point that they gave us. And you should definitely try that. Make sure you can get that. Alright, this is my little notes here before. Okay, find the average velocity from 0 to 4. Well, average velocity, by definition, is, just like we found average acceleration is change in velocity, average velocity is change in position. And plugging those numbers in, it gives me, remember that the plus c is actually going to cancel out. We've done this before. The plus c will actually, because the plus c is going to show up here and here, it's going to get canceled out. So I'm going to use my knowledge of that to make this look a little simpler. I'm 4 in here. It's 2 natural log 5 minus natural log of 6. Plus, there's the plus c, but it's going to cancel out. Minus, plugging 0 in, 2 times the natural log of 1 minus natural log of 2. C would have canceled out that one, all over 4. And let's see if we can clean that up. That's just equal to 0. So I've got 2 times the natural log of 5 minus natural log 6 plus natural log 2 over 4. And I'll leave it to you to try to figure out how, using logarithm rules, that's equal to 1/4 times the natural log of 25 over 3. You can try to figure that out. Give you a hint. Okay, in this problem we can only do part A. We don't know how to do volumes yet. It's the very next thing, or one of the very next things that we'll learn when we go back to chapter 7. So here we're just finding the area from 0 to 1 under this function. I'm going to go ahead and bring that 2 to the outside under the natural log function. Right. Now, how do you find the antiderivative of the natural log function? That's actually an integration by parts problem, but we've done it a couple of times, and maybe you remember. If you don't remember, you can go ahead and redo that. And it's it's x natural log x minus x from 0 to 1. This would be -2. Plugging the 1 in, I get 1 times natural log 1 minus 1 minus 0 times the natural log of 0 minus 0. Okay, now, actually that looks like oh no. Well, this is the oh no right here. All no, because this is an indeterminate form. We can't just say, oh, this means it's divergent. The reason we can't is because this is 0 times the natural log of 0 is like -infinity. And we know from our experience with limits that 0 times infinity is an indeterminate form. And where did this come from? It came from trying to plug 0 into this. So we actually need to think about this as a L'Hopital problem. What's the limit? We were trying to plug in 0, x natural log x. And when we plug the 0 in, as we just did here, we get 0 times -infinity. And that's no good, but we can turn it into we can L'Hopital it if we move the x to the bottom. And then we take the derivative of the top, the derivative of the bottom, and x, the -2 down here, remember that's the same as x squared on the top, equal to the limit x. So that x squared moves to the top, x squared times 1 over x is just x. So that all just turns into -x, and no problem plugging in the 0 anymore. That's just 0. So it turns out this particular indeterminate form, when I'm plugging 0 into this, it actually is equal to 0. We determined that using L'Hopital's rule here. So that's 0, that's 0. Natural log of 1, that's 0. I get -2 times -1, which is 2. So L'Hopital's rule, it comes up sometimes. You know, we've seen it come up in a couple of these problems. These are Stu Schwartz problems, not real AP problems, but they do come up in real AP problems also. Maybe not quite as subtly as they came up here, because they will often actually spell out like what's the limit, and when you see a limit and you're in BC calculus, you think probably you'll be using L'Hopital's rule. All right.